I'm quickly starting recording. I forgot to get that going earlier, so because I want Taylor to be able to see this too. Okay.
So the one in the center, this is Marigold. She is not mine. The one behind her that's short is mine, Harley.
Oh, okay. Oh.
They know I bring them horse treats, so they always expect me to feed them. But this is Harley.
Okay. Oh. Okay.
She's my old lady because she's 20 years old finally.
Wow. It's like Wild Kingdom here. Well, okay. Well, I'm sure that Taylor's surrounded by cats too. So. Okay.
Being lame. There she is.
Oh, yeah. Okay.
She's done though.
Yeah. Okay. Well, let's get the rest of you in that state too by waiting into numerical linear algebra. Okay. Let's see. Oh. I use Teams pretty much every day, and now every now and then I just all of a sudden totally forget how to do stuff in Teams. Okay. So this is our last day dealing with Chapter 5, iterative methods for AX equals B, before we get into my favorite part of the course, which is eigenvalue methods that'll start on Wednesday. Okay. Now, we've seen a few iterative methods already, but their applicability is very limited. Every method we've seen so far has only been suitable for symmetric positive definite matrices. So we've seen steepest descent, then Latex iteration, and then from there conjugate gradient. And they're only suitable for that case. So we'd like to be able to use similar ideas of the working of Krylov subspaces and search directions and so forth to be able to solve other kinds of systems. And so if there's some way we can extend that, that would be desirable. And it turns out there is more than one way to do that. Now, I actually have a lot more in these notes than A, I could probably cover in an hour and 15 minutes, and B, that you could possibly stand to sit through. But fortunately, the range of homework problems is pretty limited. So the last portion of this will not have homework problems on it. So so hopefully it won't be as people, but the notes that I post will include everything. Okay, so the way we can proceed is build a method whose goal is to try to make the residual, so b minus ax, make that vector as small as possible, subject to some other conditions. And this would be a way to extend conjugate gradient to other kinds of matrices. Okay, so all right. So with a conjugate gradient method, we define the initial residual. So we have our initial guess x naught, which is most likely 0. So then we have our residual b minus ax naught. And then we build a Krylov subspace by repeatedly multiplying this initial residual by a. And what we prescribe is that the solution at every iteration is equal to the initial guess plus some linear combination of these vectors. So does this conjugate gradient work that way? We'd like to have similar idea, but how do we get around the fact that the system is not symmetric positive definite? So what I'm going to do is so with conjugate gradient, every iteration had this form. So after k steps, our solution is the initial guess plus a linear combination of these orthonormal vectors q1 up to qk that form an orthonormal basis of this space. And then we had to find some way of choosing which linear combination to take. Now in conjugate gradient, the goal was to make all the residuals orthogonal to one another, and also make the search directions orthogonal to one another. So that ended up dictating this vector yk here. So what are we going to do if we want the solution to have the same form? How are we going to choose yk if we no longer have symmetric positive definiteness to rely on? All right. Okay. Oh, that's right. I forgot that equation references don't work in this LaTeX on the fly environment, but this is a form we're still using. So the question mark is supposed to be a 1, and it will be in the notes that I post in Canvas later. But this is our framework. Okay. Now, okay. Now here's our dilemma because of A not being symmetric positive definite. Because what we could do, we could try to do, what we did do in conjugate gradient is generate orthogonal polynomials using a free-term recurrence relation, each one dependent on the previous two. And we were able to do that because we could define orthogonality of functions using an inner product like this. Actually, I should mention, yeah, this is a mistake that I posted from a book, but I need to correct it here. That should be not B, but it should be R1. Okay, so what is this saying? This is saying that the inner product of two functions f and g is defined by this expression here. And so f and g are said to be orthogonal if this inner product is 0. Now, if A is symmetric positive definite, then this in fact defines a valid inner product, but only if A is symmetric positive definite. So if it's not, then we might have a problem where like the inner product of a function with itself might not be a positive real number, which is required to, because if you take the inner product of a vector of itself, that should be its magnitude squared. Well, magnitude ought to be a positive number. So when A is not symmetric positive definite, that may not be true. So we can't define orthogonal polynomials in exactly the same way as before. So this is the first instance in which A not being symmetric positive definite is a problem, because we're trying to generate a sequence of orthonormal vectors, and now we find we cannot do it as easily as before. So what can we do? We can turn to something that we've actually seen in another context already. Gram-Schmidt orthogonalization. Now, we saw Gram-Schmidt as a way of computing the QR factorization, that if you're given a set of vectors, Gram-Schmidt orthogonalization will make them orthonormal by linearly combining them, and that has the effect of producing the thin or economy size QR factorization. But that's going to help us here too. So how am I going to use it? So let's suppose I already have these vectors that are orthonormal, and they span my k-dimensional Krylov subspace. The question is, how do I generate the next vector in the sequence, qk plus 1? So that's what Gram-Schmidt is going to help me with. Okay. So to get my new vector, what I'll do is I'll take my previous vector, qk, and multiply by a. And then I will orthogonalize it against the previous ones. Now, the reason why this is a good idea has to do with how you define a Krylov subspace. A Krylov subspace, you take your initial vector and you keep multiplying by a. So this is the set of all polynomials of degree less than k times R1. So if I'm going to expand my subspace to dimension k plus 1, that's going to be a set of all polynomials of a of degree less than k plus 1 times R1. So I can just take a vector from this space, multiply by a. In other words, I'm bumping up my degree by 1. So now my previous vectors, q1 up to qk, and aqk already span my new larger Krylov subspace of dimension k plus 1. I just have to make this one orthogonal to all of these. So for that, I use Gram-Schmidt. So I take that vector aqk, and this is literally the Gram-Schmidt process that I compute these coefficients, so inner product of each previous q with aqk, and then I multiply that by qj and subtract it off. So now vk is aqk orthogonalized against the previous q's. Now it's orthogonal to the other ones. It's not normalized though. It's not a unit vector. So then I normalize it. I divide by its 2 norm, and now qk plus 1 is my new vector. So to confirm that this vector really is orthogonal to all the previous q's, what I'll do is, if I let I be an index from anywhere from 1 to 1 to k, so I take the inner product of both sides of this equation with qi. So I have qi transpose vk, and then I take the inner product of every term here with qi. So I get qi transpose aqk, and then in the sum I have, this is just a number. So I take qi transpose qj, and it gives me this right here. But the q's are orthonormal. So this expression is going to be 0 unless I equals j. So then I still have this term, and then all the terms went away except where I fill in j equal to I. So it gives me this. So that is from orthogonality of the q's. But the q's are not just orthogonal, they're orthonormal. So qi transpose qi, qi is a unit vector. So this is 1. So I get qi transpose aqk minus qi transpose aqk, and this whole thing goes away. It's 0. So vk really is orthogonal to all the previous q's, and then by normalizing it to get qk plus 1, that tells me that these vectors really are forming an orthonormal set. So they're orthogonal to each other, and they're all unit vectors. So at least like conjugate gradient, I now have a way of generating an orthonormal set of vectors that span this Krylov subspace. The difference is, in the Lanczos iteration, which is closely related to conjugate gradient, each new vector in this set only depended on the previous 2. It was a free term recurrence relation. Whereas here, if I look at these steps here, what I find is that my new Q depends on all of the previous ones. So it is more expensive to get it. Whoops. Okay. Oh, and now to start a sequence of vectors, all I do is I take my initial residual, so V0, that's the same as how I defined R1, is a B minus AX0 for my initial guess X0. And then I just normalize it. And then I should make clear that should be the 2 norm. And that's something that should have been made clear in the book too. Let's see. Oh, yep, forgot to mention that. Okay, this is page 186. Okay. All right. So now that I have an orthonormal basis for my Krylov subspace, in other words, if I look at how I generate my solutions here, what do I know? This is given or chosen. I now have this because these little q's form the columns of capital QK. I still don't have this. So I need to tend to that next. Okay. Now notice here, I'm computing these expressions, QJ transpose AQK. So I'm going to define this shorthand for them. Little hij is QI transpose AQJ. Then, and this is for I going from 1 to j. And then I'm going to define hj plus 1j to be the 2 norm of vj that was computed up here. So this gives me another way of expressing the orthogonalization I was doing earlier. So if I take this summation and move it to the other side, then I get this. Because, okay. Actually, what I'm going to do is I'm going to show you step by step how that happens. Okay. Okay. I got a Latex error to fix here. Okay. All right. Here's something went wrong here. Oh, I see what happened. Okay. All right. All right. This is literally copied from above, the Gram-Schmidt orthogonalization. But I want to change the indices. So wherever I have K, I need to make that J, and then J I need to make I. So, okay. So I'll make a quick notation change. Whoops. Okay. So all right, then I'm going to use this notation, Qi transpose AQJ, that's Hij. So I'll just fill that in. Okay. Then I'm going to move this summation to the other side. Okay. All right. Then Vj is the same as Qj plus 1 times the norm of Vj. Okay. And that comes from this right here. So I just replace Vj with Qj plus 1 norm of Vj, just rearranging this equation. But 2 norm of Vj is this. So now that gives me this line right here. All right. So this is just another way of looking at this Gram-Schmidt orthogonalization process. But this one's going to help me figure out how to compute solutions to AX equals B. Because now, if I write out this relationship for each j from 1 to k, then the left sides, AQ1, AQ2, etc., form the columns of A times capital QK. So I have AQK is equal to and so I have AQ1, AQ2, AQK. All right. So if I take these vectors and put them all together into a matrix, I'll have AQK on the left side. What about the right-hand side? Well, here I have a linear combination of all the columns of QK. So, in other words, this is basically a matrix vector product where I'm taking capital QK and multiplying that matrix by a column vector formed from the H's. So I put it all together and I have this matrix product. So these summations, if I write it out for j going from 1, 2 up to k, can be expressed this way. And then these terms right here, okay. All right. Well, all of these for j going from 1 up to k minus 1 will get included in this. But the very last one, when j is equal to k, I need to write separately because capital QK consists of Q1, Q2 up to QK. It doesn't include QK plus 1. So this term only affects the last column of its matrix equation. That's why I have an EK transpose here. EK transpose is a row vector of all zeros except for 1 in the kth position. So this expression right here sits in column K of this matrix. So this is a matrix. It's an outer product. This matrix is all zeros except for this sitting in the last column. because of the 1 that we have here in the last position. Okay. Now, so here I have linear combinations of the columns Q1 up to little q1 up to little qk. But here I have qk plus 1. So what I could do is think of this whole right-hand side as the matrix qk plus 1 times this matrix hk tilde. So what are these matrices, these hk and hk tilde? Hk is formed from all these coefficients, hij here. And here's the form that it has. Now, this kind of looks like an upper triangular matrix, but it's not, because there's one subdiagonal that's non-zero, and everything below it is 0. So this is not an upper triangular matrix, it's called an upper Hessenberg matrix. So anytime you have a matrix that can have anything you want in the upper triangle, in the lower triangle, you have one non-zero subdiagonal, everything else must be 0. That's upper Hessenberg. And we're going to be seeing more of these when we deal with computing eigenvalues. So that's HK that we have here. HK tilde is the same, except we have this one more entry below this one. That's a HK plus 1K. So the last row of this matrix is entirely zeros, except for this in the rightmost position. So both of these are Hessenberg matrices. This one is K by K. This is a rectangular matrix. It's K plus 1 rows and K columns. Okay. All right. So as an example, I'm going to consider the second column of this matrix equation. So the second column of the left side is AQ2. The second column on the right side, I take the second column of HK, which consists of these 3 entries right here. So I would have H12 little q1 plus H22 times little q2 plus H32 times little q3. So that would include all of this when j is equal to 2. So that would be, so I would get the first 3 columns of capital QK multiplied by these coefficients from the second column of capital HK. And then this is 0 in the second column, so it doesn't make any contribution. So this part right here accounts for everything you see here. And the same pattern applies for all the columns until I get to the last one, where I need this term. Questions up to this point? I know it's kind of weird. But it's a worthwhile exercise when I make these manipulations to like, and something you can try to do, outside of class, to try to convince yourself that these manipulations are correct. That when I rewrite something, like when I have this, but then I take this column by column, so I take all of these vectors and put them together to a matrix, that if I therefore do the same thing on the right side, these are vectors. So if I put these in a matrix also, then it can be recognized as this kind of matrix product. And the thing to keep in mind here is to help you understand these kind of expressions. Here we have a linear combination of these vectors qi. So I'll just write this down here, something to remember. Oh, spill over to the next page. Anytime you have a linear combination of column vectors, that is a matrix vector product. Okay. And to add on to that, whoops. That's a matrix product. Okay. So now does what happened here? Okay. Oh. All right. So to show you what I mean. Okay. All right, I'll do this with a simple example. Okay. All right, so if I take the sum that I had earlier, I equals 1 to j of qi hij. I'll make sure I have that right. Yeah. Okay. And I get to pick certain specific values of j. Okay. So what we have here is let's say when j is equal to 2. Dang it. I have Q1 and Q2. So this is a matrix for a matrix vector product. The vector in question is a column vector of these coefficients that are used to take a linear combination of these vectors. So that would be okay, so that'd be H12, H22. Okay. So that's what we have here. A linear combination of column vectors is a matrix vector product. This is a matrix. It consists of the columns you're taking a linear combination of. The coefficients of the linear combination form a vector in the matrix vector product. Now, that's for j equal 2. So then if I have the same thing for j equal 3, so that's going to work out very similarly. All right, so here I'll just have an extra column. Oh, wait, that should be. Oh, okay. All right, so now I have 3 columns slapped together, and then they're for free coefficients. So H13, dang it, H23, and then H33. Okay, so now what if I, and this would be, okay, so now if I put these 2 vectors, one for j equal 2 and j equal 3 together, Okay. Okay. All right, so if I put this in there for the case j equal 2, all right, so here j equals 2, and here for 3. All right. So I'd like to express both of those together as a matrix-matrix product. So here, the vectors in question come from the same set. Here I'm only using 2 of them, Q1 and Q2, and then also Q3. So I could express this as a matrix consisting of Q1, Q2, and Q3. Okay, times another matrix consisting of the coefficients. So for this first column, I have these coefficients, H12, H22. And then in this column, I am not involving Q3 at all. Therefore, that requires putting a 0 there. And then for the second column, I involve all of Q1, Q2, Q3 multiplied by these coefficients. So they would go in the second column. Okay. So this is a process by which we go from something like this to something like this, by recognizing certain expressions as matrix vector products, and then when you stack them together like horizontally, those are columns in a matrix-matrix product. Okay. Right. And this is a very valuable skill to develop, not just for homework problems in numerical linear algebra, but also it's a good research skill if you're dealing with numerical linear algebra, to be able to go back and forth between different perspectives. Because sometimes you want to work with individual entries, be down to IJ level. Other times it's helpful to look at operations in terms of larger entities, matrices, vectors, or matrix-matrix multiplication. Because then it gives you a way to figure out what to do that might be obscured if you're looking at it in a not really wrong way, but just not the way that is conducive to figuring out what your next move is. Okay. So now that we have this matrix-matrix product, we can use that to figure out how to compute iterates. Okay. All right. So here is the form of my solution. So I want to make this residual as small as possible. So here's a definition of residual. But then I did something like this with Lantros. Okay. If I write out what xk is, that would be b minus a times x naught minus A times the rest of it. Okay. But B minus AX naught, that was defined earlier to be V naught. So now we have this. But V naught is equal to its own 2 norm times Q1, because that's based on how Q1 was defined. That happened up here. Okay. Now, AQK can be expressed as QK plus 1 HK tilde. That was shown earlier. Now, so now what I can do is to get from here to here, I can use the fact this came up in a homework problem recently that the 2 norm of a vector is not affected by multiplying by an orthogonal matrix. So I take this whole expression and multiply it by QK plus 1 transpose. Okay. Well, Q1 is the first column of QK plus 1. So Q1 I could rewrite as capital Q, K plus 1, E1. E1 is what you multiply by to get the first column. QK plus 1 is orthonormal column. So QK plus 1 transpose, QK plus 1 is identity. So these cancel. This and this also cancel. So this is what you're left with. And for convenience, I define beta naught to be the 2 norm of V naught. So now, to make this as small as possible, I need to make this as small as possible. But we know how to do that because this is a full rank least squares problem. So this is the kind of problem that you can solve because remember, HK tilde is a rectangular matrix. It's K plus 1 rows, K columns. So you can solve this by solving normal equations or by taking QR factorization of this matrix. So this is something we know how to do. So now we have a way of computing iterates of this form that make a residual as small as possible. So now the method is fully described, so I can show you the algorithm. And this method is called the Generalized Minimum Residual method, also known as GMRes. Okay. All right. Okay. 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 Actually, I need to make a change of notation. Something else I remember having to correct in the textbook. Instead of beta naught, I'm going to call it H10. That way, it'll be consistent with this right here. So when j is equal to 0, this is H10. Okay. Okay, actually, I should make that correction up above. Okay, yeah. So H10 is the norm of initial residual. Okay. So we choose initial guess, get our initial residual, and then start the iteration. What we do is we get each new orthonormal vector. This is a Gram-Schmidt part, or computative elements of Hessenberg matrix H. We orthogonalize each new vector. We take our previous vector, our last vector multiplied by A, and then do all the Gram-Schmitting to orthogonalize. And then we take its norm, and then we see here the next iteration, this is where we normalize to get each new little q vector in our orthonormal set. Now, okay, I need to change this to H10. Okay. So as I define my elements of H tilde, I solve this least squares problem. My solution is the vector yj, and I use that here to construct my iterates. Okay. So questions about this process? Now, this iteration is called Arnoldi iteration that produces this orthonormal set of basis for a Krylov subspace. But now I want to tie this back to Landshaw's iteration that we see before. What if A is symmetric? So I have this relationship from before. Now, if I were to multiply both sides on the left by QK transpose, well, that would cancel this QK here. I'd have only HK. Capital QK, its columns are orthogonal to QK plus 1. That's not included in this set. So taking inner product of capital QK for this would give me 0. So on the right side, I only have HK. On the left side, I have QK transpose AQK. So this gives me a formula for HK. Now I take a transpose of both sides. So I get HK transpose, and then I have this, which is the same expression, except the A is transposed in the middle. But now, what if A is symmetric? If A is symmetric, then that is A transpose is just A. So HK transpose equals HK. So if A is symmetric, HK is also symmetric. But HK is Hessenberg too. So if I go back to show you the Hessenberg matrix, here is Hessenberg matrix. Everything below this first subdiagonal is 0. So if HK is symmetric, everything above this diagonal also has to be 0. So in other words, we have nothing left except for the diagonal, this one subdiagonal, and this one superdiagonal. That is a tridiagonal matrix that we've seen before. So I'm going to call that TK. And we've actually seen TK before. TK is a tridiagonal matrix produced by Lanczos iteration. So really what's happening is Lanczos is what Arnoldi iteration becomes if A is symmetric. And the reason why is both algorithms are doing the same thing. They're generating an orthonormal basis for a Krylov subspace. So when A is symmetric, what we could do is solve this least squares problem. I mean, in Lanczos iteration, we already had a way of computing solutions, but as an alternative, we could solve this full rank least squares problem, just like we do in GMRes. So in that case, we get a new method. It's called minres. Really, it was minres that was developed first for a case where A is symmetric. And we performed Lanczos iteration and solved this full rank least squares problem involving a tridiagonal matrix TK tilde, where TK tilde is like HK tilde. We have a one extra row. And then that method, minres, was extended to the unsymmetric case, and that's what gives us GMRes. So here I'm going backwards. I'm showing you GMRes and then saying, okay, now if A is symmetric, we have a special case of that, and that's minres. Okay. So now some comparison of the two methods. All right. Because even though one is a special case of the other, there's significant differences between them. In GMRes, as I mentioned, each new Q vector depends on all previous Q vectors. But in minres, it depends only on the previous two, because it's a Lanczos iteration has a three-term recurrence relation that generates these vectors. So what that means is when you solve a least squares problem, it's a lot more expensive to do so in with GMRes. Whereas in minres, it is possible to compute each new xk just by updating xk minus 1, kind of like in conjugate gradient. It's actually one of the problems that I did not assign, for which you should be thankful, because it is kind of painful, actually. But I just want to point out that it is possible. All right. But with GMRes, okay. What happens is each iteration becomes a lot more expensive than the last. You're solving a larger and larger least squares problem every time. So what is commonly done of GMRes is to restart it. Like, so in other words, you've performed a certain number of iterations, you computed x1, x2, x3, and so forth up to some point xk, and then you stop and use that xk as the initial guess for a whole new GMRes iteration. So you've tossed away all those Q vectors, started fresh. So that way your storage requirement does not get out of hand. So the MATLAB function for GMRes includes a parameter, if you want to specify, like restart every so often, like every 10 or 20 iterations, something like that. All right. Okay. Actually, I think that's all I have on GMRes. Yes, it is. Okay. Are there any questions at this point? I know, brains are probably fried. And some of you still have one more class to sit through. Well, PD should be gentler today. Well, I'll let you be the judge of that. Okay. We don't have a lot of time left, so what I want to do, not really going in depth, because I've already gotten to the end of like, whatever homework problems are assigned here. Okay. Let's see if it'll let me do this. Oh, I want to try to uncomment a certain portion, but apparently it's not letting me do that in this editor. Oh, okay. Oh, okay, good. All right. So quickly I want to mention Bi-Conjugate gradient method. Now, the whole goal has been to generalize the conjugate gradient method to non-symmetric positive definite matrices. So GMRes is one way of doing that, but we have a problem that each iteration becomes more expensive than the last because of this storage requirement, having to use all previous Q vectors to generate the next one. Now, Lanczos iteration doesn't have that problem. It generates each new vector from previous two. So is there a way to do the same thing in the case where matrix A is not symmetric positive definite? And the answer is yes, if you give up orthogonality. So there has to be some kind of sacrifice here. So what we do is we generate two Krylov subspaces, one based on A and the other based on A transpose. And instead of generating one Krylov subspace where all the vectors in the basis are orthonormal, we generate bases for two Krylov subspaces, and they're called bi-orthogonal. So we generate Q1, Q2, and so forth that span this space, like before. Then we generate Q1 hat, Q2 hat, and so on that span this space. And they are bi-orthogonal. So Qi hat transpose Qj is 0 if I and j are different, 1 if they're the same. So another way of putting it is if these are the Q1, Q2, and so forth for this Krylov subspace, and Q1 hat, Q2 hat, up to Qk hat for this Krylov subspace, then we have this relationship. So notice the matrices are different. Qk hat transpose Qk is identity. So then, using Gram-Schmidt, we define an inner product that's not really a valid inner product because A is not symmetric positive definite. So now we have two recurrence relations. These recurrence relations closely resemble the ones you have from Lanczos, where you're generating new vectors, each one depending on the previous two in its sequence. So like Lanczos, you get a tridiagonal matrix, but notice we have different elements on the subdiagonal and superdiagonal. So this matrix is not symmetric because A is not symmetric. So the actual algorithm, do I have that here? Yeah. If you were to compare this algorithm Bi-Conjugate gradient to conjugate gradient, you'd find a lot of similarities. It's just that certain things are duplicated, like involving both A and A transpose because of a lack of symmetry. So it's more expensive. But this is another way besides GMRes to generalize conjugate gradient to general AX equals B problems. downside is this method, as described, numerically unstable. It's crap. People have worked on it. So Bi-CG stab is a modification of Bi-CG that makes it numerically stable. And that's still an active area of these kinds of iterative methods for unsymmetric matrices. In fact, that's the topic of someone's master's thesis in here. It's a really tough problem in the general case. Okay, so I didn't really want to say too much about Bi-CG anyway, because all of our brains are fried enough, and it doesn't come up in a homework, thankfully. But I just want to make you aware of it, that this, and there are very MATLAB functions built in for all these solvers. There's one for GMRes, there's Bi-CG, and MinRes. They're all there, and there are other ones too. But these are some of the best known iterative methods for more general systems of equations. Okay, so now, so I think we've suffered enough, so I will pick up on Wednesday, getting into Chapter 6 on eigenvalue problems. Yeah. Okay, so no one's had any questions up to this point, so I guess it's probably safe to assume that there aren't any now, unless anyone has any on other things like homework and such. But in any case, I'll just I'll end the recording at this point, and then anyone who has any questions about anything is welcome to stick around in the last minutes before PDE. Oh, wait, see, we have something being typed in the chat. Oh, okay. Oh, you're welcome.